Hi guys, so today we'll be going over chapter 1.2 of computer science, IGCSE and O level both. The syllabuses are the same. So let's start. Point 1 says understand how and why a computer represents text and the use of character sets, including American Standard Code for Information Interchange, ASCII, and Unicode. So do you remember ASCII? I will just pronounce this as ASKI. Let's just say ASCII, right? ASCII for short. ASCII, ASKI. We'll just pronounce it this way. Moving on. So notes and guidance. Let's read this also. Text is converted to binary to be represented by a computer. Because before we understood that computers can only understood binary. So two values at once, either one or a zero. So that is why text has to be converted to binary so that a computer can understand the binary and whatnot. Unicode allows for a greater range of character sets. So there are two standards for character sets, ASCII code and Unicode. So note says Unicode allows for a greater range of characters and symbols than ASCII, including different languages and emoji. Unicode requires more bits per character than ASCII. So these are the points for point one, bullet points for point one. And what is a character set? What is ASCII? What is Unicode? Okay, let's get into the notes. This is again C notes. And in the earlier videos, I did realize the font size was a bit smaller. So I made it a bit bigger in this video, and subsequent videos will also be a bit bigger. So as you can see, the zoom in is at 125%. And even in the book, it's 156. At the syllabus, it's 146. You get the point. I zoomed in a bit. So what is ASCII? The standard ASCII code character sets contains 7-bit code that represents the letters, numbers, and characters found on a standard keyboard, together with 32 control codes. What is this control code? It does not matter. So main part is the ASCII code represents every letter, number, and characters. So special characters like the equal sign, the bracket, close bracket, the slash, the underscore, the question mark, all these, things that are not letters and also not numbers. So these are represented by the ASCII code. So if you press 1 on your keyboard, there is a subsequent ASCII code. Let's just say 75 is the ASCII code for the value, the number 1 on your keyboard. When you press 1, the value 75 in binary, yes, in binary sent to the computer. So the computer says, okay, we have received the binary value 75, and then the character matches, the binary value 75 with its own ASCII table. And then the computer can relay, okay, so the user has pressed the keyboard number 1 or the number 1 on the keyboard. So this is how ASCII character code works. And uppercase and lowercase characters have different ASCII code values. So as you can see over here, A is represented by a 65 and small a is represented by 97. So uppercase and lowercase characters look different and you may use them in a different scenario. So they are differentiated by a different value. Okay, so every subsequent value in ASCII is the previous value plus 1. So you have A, which is 65. What if you need B? So if you need capital B, you will use the value 66. If you use 66, then capital B will be the subsequent letter for your value. So here is one more example, e.g. A is 97 in ASCII. B will be 98, which is 97 plus 1. So basically, if you want to go like A, B, C, D, E, F, G, right? You just take A and then plus 1, plus 1, plus 1 until you reach E. And important ASCII values to memorize. So you do not generally need to memorize this. You know, if a question like this even comes, the question paper will give you one value. Let's just say the value of A will be given. They say, okay, find out the value of capital E, right? So you just have to know how ASCII works, and if the value of capital A is given, you can find the value of capital E pretty easily. ASCII uses one byte to store the value. So what is a byte? We understood. A byte is basically this eight, you know, binary values. So it could be a 0 or 1. So one byte is 8 bits. So the letter A will have 8 bits associated with the letter, and these 8 bits will store a number or an integer value. So yeah, one ASCII value has 8 bits inside it, or it needs 8 bits to store. When ASCII value of a character is converted to binary, it can be seen that the sixth bit changes from 0 or 1 to 0 when going from lowercase to uppercase. So a lowercase a, the sixth bit will be this one, and it becomes 0 when it is uppercase. Okay, understood. And the rest remains the same. So, okay, cool thing to note. Do make a mental note if you want. Then comes Unicode. What is Unicode? So there are two types of character sets we learned. One is ASCII, one is Unicode. We looked at ASCII, now we shall look at Unicode. ASCII does not contain all the international language, thus Unicode is used to solve this problem. So ASCII can only represent the English language and a bunch of unique letters such as the equal sign, the bracket, the closing bracket, the comma, and whatnot. So something like Chinese will not be supported in your normal keyboard. So we need to also add Chinese to the ASCII character set. And the ASCII character set is a standard. So if you change the standard, right, the computers created before the change will have to be updated with the new code and whatnot. So cross compatibility will be destroyed, and so this is a big hassle. So we just made a new character set, which is Unicode. So Unicode supports up to 4 bytes per character. 4 bytes per character. How many bits is that? One byte is 8 bits. So 4, 8, 32, right? 32 bits per character. ASCII only supports 8 bits per character. As you can see, 8 bits here. So basically, yeah, 4 times the amount of information. Not exactly 4 times, it's much more, but 4 times the amount of bits. The information it can store is like a lot. Let's just say 64 times or something like that. I'll have to calculate to find out the exact number. But it can store many times more information than ASCII. Unicode can store many times more information, showing multiple language and more data. To represent text in binary, a computer uses a character set, a collection of characters, and the corresponding binary codes that represent them. So if we look at the board, sorry for the flashback. So if you look at the book, there is mentioned character set. What is a character set? All keyboard characters that can be represented by the keyboard, and their binary values are stored in the character set. So no need to memorize. I mean, it's kind of memorization, but you just have to understand what is a character set. So a set of Apple, let's just say a set of, I don't know, books. So this set includes a lot of things. Yeah. So the set basically means all the characters that can be represented by the keyboard, and their ASCII values 75, 65. These are the ASCII values. So all keyboard characters that can be represented by the keyboard and their ASCII values are stored in the character set. This is what a character set is. You need to memorize that, just so you know. Do ask the question, define a character set, or what is a character set. So that is Unicode and ASCII code completed. My bad. So that is Unicode and ASCII code completed. Now is text, sound, and images. So next will be, I guess, sound. Yeah. So let's look at the syllabus. Understand why a computer represents sound. Why and how, yeah. Why and how a computer represents sound, including the effects of the sample rate and sample resolution. Okay, so bullet points starting from here. A sound wave is sampled for a sound to be converted to binary, which is processed by a computer. So keyword being sampled, the sample rate is the number of samples taken per second. Okay, so number of samples you take per second, another keyword. The sample resolution keyword is the number of bits per sample. Okay, the accuracy of the recording and the file size increases as the sample rate and resolution increase. So accuracy increases as you increase the keyword and keyword. Okay. Let's understand the keywords one by one. First of all, a sound wave. What is a sound wave? Okay, let's get into that. It's sampled for sound to be converted to binary. Sound wave is sampled. Okay, let's draw this. So if you have O-level physics or IGCSE physics, there will be a chapter called waves, and you will understand or learn about light waves and sound waves, transverse, longitudinal. And sound wave is basically can be represented by a literal wave or like this. So if someone speaks, there is a person standing here and they speak, right? They speak some words. You can represent this by this kind of waves, right? Sound waves are coming, but you can represent it by in another way. So this wave is also a sound wave, and this will also be a sound wave. We will see this sound wave, yeah, because this and this both are same. Both are the same sound waves, just represented differently. So this sound wave, you need to convert it to binary and store in your computer. This sound wave is analog in nature. What do I mean by that? This is in the real world, and it is basically a bunch of particles vibrating and hitting each other and carrying the sound forward. There is nothing electrical or anything about it, right? You cannot store like, a bunch of particles are moving in the air and they are carrying the sound with it. So you cannot store this in the computer. You need to convert it to electrical signals. So this is the main point. Convert something analog which is not electrical to a digital electrical signal. This is your job now. And how do you do that? So you take a measuring device. Let's just say a microphone. So let's just say you have a microphone here, and this microphone will measure the sound waves. How does it measure the sound waves? There will be a plastic circular disc, and this disc will be attached to a magnet. So a magnet will be attached here, and this magnet will vibrate with the plastic because when the sound hits it, right? The sound hits it, the plastic disc will vibrate because the air particles make it vibrate and move. When the plastic disc moves, the circular magnet, right? It will move this way and then back this way, right? So when the magnet moves, there is a coil around the magnet, right? This coil will be around this magnet, and this coil will pick up the electrical signals and transfer it to a digital converter or something like that. Then it will be connected through USB or some other means to your actual computer. So basically remember this: a plastic disc, magnet, then some copper wire, and this copper wire will just convert it to electricity. And this electricity, let's just say, has a certain amount of information stored into it. And this information is stored digitally. So how do you represent this wave digitally? Basically, you take measurements, right? Why do we take measurements? Because look at this wave. This is bending up and down. And let's go back to another example, which will be look at the Earth. If you zoom out, right? If you're looking from the moon, let's just say you're looking from the moon, you can see the Earth is round. But if you start zooming in and in and in, and if you like zoom in into the surface more and more, the Earth will get like flatter and flatter until it becomes completely flat. It will appear flat to you as you are very zoomed in. So this wave is the same thing. As you zoom in and in and in, it will just you can just keep zooming in because this wave this wave has an infinite amount of information stored into it, right? If you cannot store the complete sound wave in its entirety because it has infinite amount of information. You cannot store an infinite amount of information. So you only take select measurements in each wave point. Let's just say you take a measurement on here, measurement here, and so on and so on. You take measurements periodically, so you can have an estimation of how the sound wave actually was. So this is how you store the sound wave. And this, in the digital form, a sound wave will look like this. So it will look like this. So as you can see, it's I don't know, it has a lot of edges, sharp edges. Why? Because now you can actually draw the wave on it like this. The wave is approximated, right? This digital wave is an approximation of the analog wave. It cannot completely replicate it, but it can, kind of approximate it. So when they mean by sample, keyword here, a sound wave is sampled. This is basically meaning measurement. So as time goes on and on, so this will be a time axis t. As time goes on and on, you will take a measurement over here, measure the amplitude meaning basically how high the wave is or how loud the wave is. Then you measure here an amplitude, then again here, and then you keep measuring the amplitude after, let's just say, 1 millisecond, 1 ms. Every 1 millisecond you measure the amplitude and see how loud it is, and you just store the loudness value from, let's just say, 1 to 100, right? You assign this 1 to 100 numbers to the loudness value, 100 being the maximum loudness you heard inside the wave. So this will be the maximum loudness, and this one will be the minimum loudness anywhere here where there is a minimum. Let's just say here is the minimum loudness. And so basically this is how you store the digital value in your computer. You measure the wave over and over again, how loud it is, and the amount of measurements you can take every second is the sample rate. If you measure every 1 millisecond, that is a lot. There is like 1,000 measurements each second. So that is sampling rate or sample rate, number of samples or measurements taken in a second. Then there comes sample resolution. So remember the numbers, right? We assign numbers to the loudness, how loud a wave is. And this is the resolution. If you have a lot of numbers, let's just say 1 to 1 million, right? 1 to 1 mil. So if you have 1 million numbers, then I don't know, the loudness value, right? You can represent that pretty easily. Let's just say you have two loudness values, only two. So you have 1 and 2, let's just say. We will not use 0 here. So what if now you measure a sound wave of a aeroplane, a car, or something like that? And this basically means all the things, right? The aeroplane, a person speaking, and a dog barking, right? The whole thing will be in one sound wave. So when you listen to the sound wave, you will only hear first the aeroplane is flying, and then let's just say the dog barking or something like that. You will only hear two loudness values. You will not hear someone talking. You will not hear the car going or anything else because it has only two values. So the amount of numbers available to the sound wave, right? The more information the sound wave can store. So this is the resolution. Think of it as a picture. The more resolution the picture has, the more clear it is, the more clear you can see. If the resolution is lower, it is more blurry and you cannot see anything. So basically, it's same as picture resolution, same as picture resolution. So sampling rate, number of measurements or rate samples per second. My bad, sorry. Number of samples taken per second. And then what is a sample? A measurement. The accuracy of the recording and the file size increases as the sample rate and resolution increase. Okay, so the accuracy will increase of your sound, and the file size will also increase if you increase the sample rate and resolution. Sample rate is number of measurements. If you take more measurements, right, you will get more numbers and you have to store the numbers. So file size will increase and accuracy will increase because the wave will be more similar. The analog will be more similar to the digital wave. And sampling resolution, right? More numbers available to each sample. Again, more resolution. But then again, larger and larger numbers will be generated. So file size will increase. So these are the notes. You can actually, pause it and try to read it if you want. And I think I mentioned everything more or less. And so I'll not be reading this out loud. So let's just say sampling rate only for a second. Number of samples per second, which is measured in hertz, HZ. So HZ I did not mention, but you probably know. Sound has a frequency which is measured in hertz. So more or less that is it. Now we'll move on to images. Understand how and why a computer represents an image, including the effects of the resolution and color depth. So resolution, color depth, how and why. An image is a series of pixels that are converted to binary, which is processed by a computer. Okay, pixels, keyword, and these are converted to binary. The resolution is the number of pixels in the image. So again, resolution and pixels. The color depth keyword is the number of bits used to represent each color. Okay, color depth meaning number of bits used to represent each color. The file size and quality of the image increases as the resolution and color depth increase. Again, as you increase the resolution, as you increase the sampling rate, let's just say for sampling rate of the image, then the file size will increase. So let's understand this. So let's read the notes for this. So first of all, you need to know a concept called bitmap images. Bitmap images are made up of pixels. A bitmap image is stored in a computer as a series of binary numbers. So what is a bitmap image? Basically, why does it why is it called a bitmap? So imagine a big square, and this will be one pixel, one pixel, one pixel, one pixel, and so on, and you can fill the whole square up. This one pixel can be, let's just say, black. So this will be one, and this will be black, and this pixel will be zero, so this will be white. And let's just say this is black again, this is black again. So this is a bitmap image. It's a map because more or less it is spread out like a map, and I don't know why it's called a map. So bits, because bits are used to store the pixels value, and image because it's literally an image, it has pixels. So bitmap image. Then what is color depth? Color depth, the number of bits representing each color, is called a color depth. In my image, we have either black or white, so either 1 or 0. So basically 1 bit, right? Let's just say in this pixel, we can store 256 different colors. So red, green, blue, yellow, and variations of yellow, every shade of yellow or green. So 256, we will need 8 bits. 8 bits to store 1 pixel. So the bit depth, right? Bit depth basically meaning, let's just say this is your screen and this is 1 pixel. 1 bit basically meaning it can have one color will fill up. And if the bit depth is lower, the literal depth of the pixel, imagine, the depth will be lower. So it will have a lot of colors inside it, and the colors you want, you can just represent on the top. Just think of it this way. It will be very deep. It has a lot of colors, as the bit depth is 8 bits, which is a lot higher than 1 bit, 8 times more. So yeah, the color you want will be on the surface. If you want the color here, it will be on the surface. This is bit depth. Each pixel and the amount of color one pixel can store. You can rate this if you want. So 0 or 1, increasing color depth increases the size of the file when storing an image. Well, this is kind of self-explanatory because, you know, let's just say there are 64 pixels in this image, right? From diagonal to diagonal, 64 pixels. And let's just say one pixel has one bit, right? So then 64 pixels will have 64 bits, and you can store the whole image in just 64 bits. But what if you have 8 bits per pixel? So 8 into 64, and that becomes like, I don't know, 1024, right? So that will be a lot, I don't know, higher, or 512, I guess. I don't know. So imagine it becomes 512, right? 64 and 512, that's a lot of, lot higher increase than, let's just say, if you used 1 bit, I could go and use 2 bits. You could represent more colors using 2 bits per pixel. The file size will not be that small, bigger. It will just be 128 bits. So if you use 8 bits, the file size is a lot bigger. And imagine this, if you use 1 bit, you can store 8 of these photos, right? This photo, you can store 8 of the copy, or use 8-bit color depth and just store 1 copy of this photo. So a trade-off between how many colors you can represent and how many, photos you can store. Let's just say your hard drive is pretty small, so you will just use 1-bit color. If your hard drive is pretty big, then use 8-bit. Your image will look nicer. So image resolution. Image resolution refers to the number of pixels that make up an image. For example, image could contain this into this pixels. Photographers with a lower resolution have less detail than those with a higher resolution. When a bitmap image is blurry or fuzzy due to having low amount of pixels, it pixel it in it, or when zoomed in, it is known as pixelated. So a question may come that a photographer has taken a photo and it is blurry. Explain why it is blurry. So you have to write this J. It might have a lower resolution or it can be zoomed in. And then another question might come, a photo is pixelated. So why is the photo pixelated? Then you will write either the photo is zoomed in, or it has a lower resolution, something like this. And the resolution, I think anyone studying computer science will probably know what resolution is. You might have a computer in your home, or a laptop, or a phone, any device with a screen on it. You might have used it, and you know what resolution is. Anyone who doesn't completely know yet, the image I dream, it has total of 64 pixels, right? So let's just say that my image was 8 pixels long, right? 8 pixels in here and 8 pixels wide. This is wide, total has 64 pixels. So what will be my resolution? 64 pixels. Uh, this is the image resolution. Correct? Image resolution will be 64 pixels for my case, but here it is 4096 by 3072. So very sharp image. 4000 pixels by 3072 pixels long. So 4000 pixels long or something, or 3000 pixels wide, right? So imagine 4000 in just one line and 3000 in just one line. And then if you multiply these two, you'll get so many pixels on your whole image. And I guess that is it. A short recap of the points would be, the image has a series of pixels. So, if you think about the sound wave, you sample the sound wave at each second. And for the image, you, let's just say, took the image of this part of the page, right? You will take a sample here, and just measure the color value in this sample. And if you take the color value in this sample, you will realize this is actually white and this is actually some kind of, I don't know, pinkish, reddish color. So sample rate or sampling a sound wave, right, has the same equivalent thing for an image. You just sample area, the area of an image, and then you get pixels. So one sample is called 1 pixel, and these are converted to binary to process by the computer. The resolution is the number of images. So number of pixels, here a bunch of pixels, and in this line there will be a bunch of pixels. Multiply these two, so you'll get the total number of pixels in each one column. Color depth meaning basically, as I showed, if you had one color, let's just say you can store two colors in here, and this will be a screen. Whatever color you want, you will show at the top. If you had 8 bits, there will be so many 256 different colors. You will store all the color here, and the screen will show any color of the 256 you need. So as it more deep, it will store a lot of more information. This is just a example. The screen actually does not work like this, right? So it is much different. The screen only has one LED, and this one LED will emit all the light. And the file size will increase if you increase the resolution, as more pixels are needed. And if you increase the color depth, again, more numbers will be needed to store each color. So that covers chapter 1.2. Chapter 1.3 is pretty long, and yeah, we'll cover chapter 1.3 in the next video. And did we miss anything? So this is the book. I'll just quickly scroll through it, so you can pause if you want and read it. So yeah, that was all for today, and next video we'll probably try to go over chapter 1.3. So yeah, goodbye.